let's talk a little bit about the next decade of software. So my name is Richard Campbell, as Dylan said. I make a lot of podcasts. Any .NET Rocks listeners out there? A couple of hands here now, that's awesome. So my friend Carl Franklin started the show .NET Rocks back in 2002, before the word podcast existed. We called it the Internet Audio Talk Show for .NET developers. And this week we'll publish episode 1924. So we publish every week, thanks. We talk to luminaries, folks like Dylan and many of the other speakers you have at the show about what they're working on inside of .NET, just the things that we think .NET developers need to know more about. I also make a show for sysadmins called RunAs Radio, which I've been doing since 2007, so there's about 950 of those. And for a brief interval, we made a show called The Tablet Show, where we weren't sure where tablet and mobile development should go, so we had a standalone show for that, eventually rolled it into .NET Rocks. So my advantage is I've had 20 years of talking to really smart people about what they're working on in technology and where they think things going. And it's helped me to sort of craft an idea looking forward into the future. But predicting the future is hard. And we have problems with estimating. It's a tricky thing. So I'll reference a Gates quote, this idea that we always overestimate the change that'll happen in 2 years and underestimate the change that'll happen in 10 years, which is why I said this is a 10-year time horizon. Because real change can happen in 10 years. It already has. If you've been working in this industry for a while, you've had that experience of things are simply different now, but it didn't happen as quickly as you thought. By the way, this quote is often attributed to Gates, but he was actually quoting another computer scientist, a guy named Ray Amara from Stanford University, who was making this statement in the 1960s about computing and the impact of technology. So there are many repeating themes out there. I don't believe that history necessarily repeats itself, but it does rhyme. And so where we can find alignments, we can finally find some opportunities. So if we're going to talk about software, we've got to talk about where our software runs. And I don't know if you've noticed, but the past 10 years, almost 20 now, the cloud has been a dominant concept. This idea that we can rent computing by the minute or by the hour. Today, it's not that big of a deal. I mean, we were only talking about it in 2008, 2009, 2010, and at the time, we were very excited about the revolution. For someone like me making all those podcasts, I was looking for folks that were actually doing it. For a while, there were not many people doing it, but they sure were talking about it. And then, a decade on or so, you're doing it. Now the argument is, does it make sense to not run in the cloud? Not should we run this in the cloud? And everybody's experiences are slightly different, but there's no question the cloud has come to the world, whichever flavor you like. And so we have a lot of choice there now, and it gives us different ways to think about how we write our code and where it operates. The client has also changed. The smartphone has won, for better or worse. Again, in a relatively small period of time. Before 2007, before the iPhone, phones were kind of fun, but they were pretty weird. The idea that everybody would have a smartphone is only a little over 10 years old, really, 15? That's about it. And the reality, of course, is this is now the primary computing device of most people in the world. There are over 4 billion smartphones in operation on this planet right now. That's roughly one for every adult human. Now, we, as technology folks, use our phones somewhat differently from somewhere in a more less developed area. Like a farmer in Rwanda has a smartphone, but primarily uses it to deal with weather concerns around his crops. Cost him a lot to get that phone, but he still uses it. So it's everywhere. We are all cyborgs. We have electronic extensions to ourselves. It looks like a slab of flat black glass. Now, most of the time we think cyborg, we think science fiction, and the electronics are supposed to be on the inside. But first, ew. And second, that impairs upgrades. So keeping on the outside is efficient, but looking at the reaction of the average person to misplacing their phone, it's not that different from losing an arm. So yes, we are all cyborgs. And we expect pretty much instant communication anywhere in the world, and to never, ever, ever be bored again, because there is always Candy Crush. And the consequence of this cloud and these smartphones is, of course, we have a lot of data. Some call it big data. I could call it other names. But yes, we have access to more information, some of it of questionable quality, most of it of questionable quality, but there's lots of it. Now, this is not a lot of predicting, right? This is pretty straight up. The line goes up and to the left, up and to the right. More devices, more compute, more data. So if you really want to start talking about what's going to change in the next 10 years, what's going to be different for us as developers, let's look at some limits that we're starting to hit. Starting with our friend Gordon Moore and Moore's Law. Now, Moore did not call this a law. It was an observation. Now, Gordon Moore was a scientist and a technologist, and he left Fairchild Semiconductor to form Intel. And at the time in the 1960s, Intel was making RAM. Before that, RAM was largely ferrous coils. You know, a K would be a grid about this big, and so making integrated circuit RAM was a big deal. And that's when Moore made his observation that with a lot of effort by a group of people, they could double the number of transistors on a piece of substrate for the same amount of money, roughly every 18 to 24 months. That was his observation. Other people called it a law, but a law does it a disservice. Gravity's a law. You kind of can't miss it. But this effect of doubling the density of transistors every year represents a huge number of people working extremely hard. And if we look at it from the context of transistors in CPUs, you get a graph like this. Going back to the 1970s with the Intel 4004, up until just a few years, recent times now, we've got a pretty solid line, but only when this vertical axis is exponential. If I make it mathematical, I get a hockey stick because the big numbers are so big, they overwhelm all the other numbers. It's not a good way to describe what's happening with Moore's Law. So let's find a better way to explain it to people. Anybody seen one of these before? Any ideas? Is that a warp drive from the Enterprise? No, that's this. This is a Cray 2 supercomputer, circa 1986. Back then, it cost you about 16 million US dollars. It was liquid cooled. It's curved to keep the wires as short as possible to minimize the effects of the speed of light, right? 200 kilowatts of electricity, so it needed a fairly good power supply. There was only a few hundred of these ever built. Universities, large governments, that was about it. They modeled nuclear explosions with it, and its processing power at peak operation was 1.9 gigaflops, or just shy of 2 billion floating point operations per second in 1986. Fast forward 25 years, the iPad 2. 800 US dollars when released in 2011. Don't put in any liquid, that would be bad. Runs on a battery, 1.9 gigaflops of processing power. And you play Candy Crush on it. You give it to children. So in 25 years, we went from the highest performance computers in the world to a toy. Not bad. That's Moore's Law. And it's not that fast, right? That's 2011. It's 2024. The fastest consumer compute device you can probably lay your hands on right now would be an RTX 4090, right? If you're a crypto miner, this is a very popular gizmo. Or you play high-end games. They're about 1,600, depending on how well you do looking for the pricing. 16,000 compute cores inside of it. 82 teraflops, or about 40,000 times faster than that iPad 2, and about 450 watts, like 5 times the power of that iPad as well. So I hope you got a big power supply in your machine. Don't get 2 of them. And that's a commercial device. We could buy this at a store, just, at the mall nearby. In theory, they have any in stock. Biggest supercomputer in the world right now is the Frontier supercomputer at the Oak Ridge Laboratories in Tennessee. There's about a dozen real high-end supercomputers. There's kind of a duel going on right now for the fastest machine. The Japanese have one, the Chinese have one, and the Americans have one. The Americans is currently on top. So this is based on the Cray EX architecture. It's a massively parallel machine. $600 million. So save up. 20 megawatts of electricity. So bring your own nuclear reactor. Takes up about 700 square meters, so probably not going to fit in the apartment. 1.1 exaflops, or 1,100 petaflops. So that is 13,000 times faster than that 4090, or 600 million times faster than the Cray XMP or the iPad 2. So this is the outer edge of supercomputing as it stands today. It's done with massively parallel, huge numbers of cores, but they have a new version coming called Aurora that should tip the 2 exaflop number. In the meantime, Moore's law is ending, right? This graph can't continue like this. In fact, actually, if I put in the last couple of years, you'd sort of see it starting to angle off as they're struggling to keep the chip density up. Intel's been having problems. Other companies are coming with new techniques to try and improve it. But the issue here is we're getting down to the single-digit nanometers for some of these chips. And so we take electron tunneling microscopy to look at them. This is the IBM 5 nanometer process. And you start to have interesting questions about how small a nanometer is. A billionth of a meter is a hard thing to imagine. But with some of the best imaging, we've got to the point where we can actually image individual atoms. Those yellow bumps are silicon atoms. They're 111 picometers across, 1.1 nanometers. You can fit about 40 in a 5 nanometer piece of substrate. Now, in reality, we use 3-dimensional structures and there's a bit more shape and so forth, but we're getting low on atoms. And that's a tough number to beat. And it's not just being possible to make it this way. The blue holes, by the way, are the phosphorus that make it a doped piece of semiconductor silicon. This is P-type silicon, for those who are into that sort of thing. But we're talking about 3 nanometer processes now, and you just don't have a lot of atoms to play with. We're not going to get around this. There's only certain things you can do. And it's not just, is it possible, but can you make it cost effective? Can you manufacture millions of them? Right? That's our expectation, is tens of billions of transistors on a piece of sand the size of your thumbnail for less than $1,000 US. It's an astonishing expectation. And so Moore's law running down sounds like bad news. From years ago, as developers, we pretty much built our software based on what the next machine to be released be done. Back then, when we expected to spend 18 months to build a piece of software, you could kind of anticipate the next generation hardware for it. This is how Microsoft built Windows, is they would expect that the next version of Windows would run next generation hardware, which could provide additional performance, so we didn't worry about how slow it was during the beta cycle. We don't expect that anymore. And part of the side effect of this process has been that we've largely not improved chip architectures very much. We've kind of patched them. So the Intel architecture has gotten to a point now where it's extremely complex. There are pieces in the Intel architecture that go all the way back to the 80s. Now compare this to an ARM design, because ARM has started much later, and so its design is essentially simpler. They started at 32 bits, not 8. And so they just not had to kind of patch and patch and patch. So one of the upsides to Moore's law ending is we don't have this tyranny of we'll always have a new processor, always have a new processor. We can actually improve architecture. And you're starting to see the effects of the highest performance machines now coming in ARM architecture. You can't argue with Apple's M3 and M4 processors. They're down to the 3 nanometer process now, which is incredibly small. You're talking 25 billion transistors on that substrate, and not just a processor, but also a GPU and a neural processor and a huge amount of cache memory. So that this is a very highly integrated compute. And arguably for a long time was the very best processor. Snapdragon, Qualcomm has now made their X Elite series, which is kind of batting at the same level, where they're running billions of transistors in a 4 nanometer process and also having an integrated GPU and an NPU, the Hexagon NPU. So we're in interesting times that we can't count on Moore's law to give us more compute the normal way. Instead, we're building more cores, we're integrating them more tightly, and we're optimizing architectures. In a lot of ways, it's going to be hidden from us as software developers, but we're going to be able to take advantage of that. It's also starting to shape the cloud, because the cloud is now going to specific optimizations. It's not just Intel chips and AMD chips anymore. You can run on an ARM processor inside the cloud if you want. You can rent ARM VMs and do your operations there. So we're starting to get to a place where, as developers, we're going to pick and choose the environments we run in based on architectures that give us optimal experiences. Now, that sets the stage for a certain amount of hardware, at least on the back end, and this largely is known stuff. We're not pushing too far into the future. And for the most part, when it comes to programming, the web seems to dominate, but we have a set of languages that we love, right? Yours is probably up here, right? Each of them has advantages. Python's an easy language to learn, super beginner friendly, great for data science. I find myself writing more Python these days. JavaScript is the lingua franca of web development. That's certainly never going away. Java in the enterprise, along with C#, and of course C++, because it's never going away. And same for more modern languages. So Kotlin, modernizing Java development. Swift, because iOS and Mac are their own thing, and we got to learn those things. Golang, built by Google, focused on being cloud-native development. So we're starting to build languages to reflect the platforms we're operating on. We tend to see bursts of language development as our platforms change. And so Rust is very hip at the moment as a type-safe C++, very performant way to program. And I wouldn't ever ignore TypeScript because it makes JavaScript better for a lot of folks. If you need to build sustainable web apps that can be maintained by different groups of people over a long period of time, having a little static type checking when you go to deploy makes a huge difference for folks. So many of these languages have been around for a long time. This set I put up because they're all relatively recent. And the iteration of new languages has sort of tapered off again. As we've made this shift to the cloud and we've abstracted architecture, we're seeing consistent patterns. On the web side, browsers aren't going away. For better or worse, the administrator in me likes browsers because they're already on the device. I don't have to install anything. It already has a security context. A lot of development is being done that way. The innovation you see in this space are the frameworks that underlie them. Some of these are getting older now. Angular's been around quite a while. There's still a few new ones, although I would argue this is tapering off too. That we're kind of in a stable time in JavaScript development because the language is pretty mature. People aren't adopting a lot of the latest features because they don't need them. They're being productive enough. The progressive web app has been around for a number of years. Most people only use this up to the degree that they make sure there's an icon on the person's phone, right? That's in the manifest so that people will click on it. They don't know it's a web app, just that it comes up like an app, even though it's running in the browser context. There's many other capabilities in the PWA. We just don't tend to think about them. We use the thing that matters most to us. And I'd be remiss if I didn't mention our friend Steve Sanderson, who works for Microsoft, who grabbed onto WebAssembly back in 2016, found a weirdo version of C# and made it run inside of the browser and blew everybody's minds. It was so weird that it scared Microsoft, and they kept it as a research project for about 4 years, waiting. They didn't want to attack JavaScript. And so they waited until Golang shipped for WebAssembly. Then they shipped it and called it Blazor. And I'm sure there's a few Blazor sessions at the conference that over the next couple of days if you want to take this in. Popular in the Microsoft space. Same for .NET. .NET's gone through a remarkable rewrite starting back in 2014 where they became open source and cross-platform. .NET started out in 2002 as an enterprise alternative to Java for Windows developers. That's what it was for. And then in 2014, they chose to become cross-platform, open source, designed for cloud. They did it without replacing the tooling, which is kind of crazy. And Microsoft's struggling to make smart client matter. There's many different client stacks in this space, and they have tried to consolidate them under the MAUI platform so that they have both phone development and client, regular desktop, laptop development all on one umbrella. Customers largely don't care about this. Customers only care if their app runs on their device. They don't care about other people's devices. We care about other people's devices. We want to write it once and run it everywhere that people need it. And so it's going to be an ongoing struggle. It's very hard to write software that way. If you've been writing software for some time, you know that we had many years where the device that we wrote our software on was the device that our users were going to run it on. And that's largely not true anymore. Today, we tend to write software on a laptop or a desktop that runs on a phone. Programming on a phone, not fun. But the cycle of writing in a PC to run to a phone or on a Mac to a phone is a longer cycle. It's more difficult to develop on. It's harder to understand, and phones are not uniform, right? We have a diversity of devices there too. They're all different. And so there are many efforts going on to try and solve the client problem. For me as a podcaster, the fact that I can speak to so many different groups of people about so many different libraries on the client side development speaks to this is an unsolved problem. Same for these no-code, low-code solutions. And I mentioned Microsoft specifically with their Power Platform, but it's not the only one. There's about a dozen of them. Again, that to me indicates this is an unsolved problem. For a forms over data application against data in the cloud, these products are powerful and fast and aimed at the domain expert rather than the developer. So they can't do everything, but they can do a lot of things. Enough things that folks are grabbing onto them and running with them and making messes along the way, stuff that often us as developers have to clean up or the administrators do. But it shows that we've not been able to get to the bottom of our to-do list. There's many more projects to be built, and that list is only getting longer. There's not enough of us, there's too many problems, and so these new tools are emerging to try and address that problem with less programming resources. Is it going to eliminate programmers? No. Is it going to take some pretty simple work off the table? Yeah. And the better tools allow developers to contribute additional features to it to make it faster to do, so those constrained developer resources don't have to spend as much time building software. Microsoft tried to call it fusion development, and everybody hated it. So well done, Microsoft, for more bad names. But if you look around in the no-code, low-code space, you're going to find OutSystems, Appian, QuickBase, the Salesforce platform, Oracle's got one, Microsoft. This is an area that's going to grow further. It's in its early phases, and it's because of the move to the cloud, means data is more uniform, clients are web-centric, and you can generate an awful lot of that infrastructure. So it's going to be something we're going to interact with as developers as these domain experts emerge. This is not an unprecedented pattern. We saw this back in the Visual Basic Access days as well, where domain experts, not professional developers, used those tools to do automations, and then that became their job. And hopefully they grew up as developers. Maybe that was your path into software development, different people coming in from different ways. But this is another iteration of that. Same with the move towards containers. Now, this has been a bit overhyped. The Kubernetes, all the things is a bit much, but the core concept is important. We found a new way to encapsulate software that minimizes the size of the footprint and controls the amount of interactions between them. Most of the pain in our lives around software involves different pieces of software interacting with each other in unexpected ways, and containers are a way to suppress that or manage that with a manifest. So we are seeing containers drop into the plumbing more. More and more operating systems are running intrinsically with applications in containers. For us as developers, that largely says we're just going to have to provide manifests for how our applications are allowed to communicate out of their container. And then back on the cloud side, we have a lot more tooling around all of this. You're seeing more tools around virtualized desktop and the like, and it's all about trying to make the system more sustainable. Right? There's always an old piece of software people need to run, and it creates problems. We're still having security issues. These are all technologies to try and address all this. And if I feel like I'm racing through a huge gamut of things, it's because I am, but it also feels a bit overwhelming. I mean, I have the best job of all. I get to talk to experts all the time and sometimes get to share that information with folks. But my job is to stay up on this and help organize it for other people to still think about it. You've got real work to do. You've actually got to build some of these things. And so if you're feeling overwhelmed, that's okay. It's fair. And you don't need to use every new thing. There are plenty of great careers out there where folks focus on a stack, become an expert in a stack, and work that stack for most of their career. If you want to jump on the new thing, want to change again, awesome. I'm glad you're here. This is a place to learn about new opportunities and get some ideas of what you might be doing differently. But if you're not ready to change to the next stack, don't feel badly. There are great ways to work with the stuff you've got. Keep learning. Become more expert in the stack that you care about, where your opportunities lie. And if you're ready to learn some new ones, we got some new ones for you as well. Let's change gears and talk about artificial intelligence. And I use a picture of HAL for a reason. If you were at the appetizer last night, who was at the appetizer last night? I talked a little bit about this. In 1968, Stanley Kubrick made a movie called 2001: A Space Odyssey. Arthur C. Clarke was the author of the book published afterwards, and in it there was a computer called HAL, who was artificially intelligent. That was the first time that phrase was used in public, and then of course he tried to kill everybody, setting up a relationship with artificial intelligence. At that point, the term was already 10, 15 years old, and it was a marketing term to convince the US military to spend money on software. The hierarchy of AI looks something like this. It's sort of an umbrella term for a bunch of different technologies. In fact, you'll also find that generally speaking, if it's called artificial intelligence, it's because it doesn't work. When it does work, it will get a new name, right? It'll become an expert system or robotics or image recognition. So when someone tells you, I have AI technology, you say, oh good, you have stuff that doesn't work. Because if it did work, you'd call it something else, like a large language model. Now, if you want to incorporate some of these technologies into your software, feel free. Image recognition systems are very powerful. Just make sure you do your testing. Sometimes silly things can happen. And it's important to remember that there have been technologies under that umbrella, although again, AI only became vogue again with this latest wave. Previous to this, we just called it machine learning because that's largely what it was. But it really started with GitHub Copilot. So OpenAI was doing their thing. The early version of GPT-3 came along, and they're just down the road from GitHub in California. And so they got GitHub folks got a license for GPT-3, and they experimented with the publicly available data sets inside of GitHub, and we got this Copilot 2. It's a very cool name, which is why you know Microsoft didn't think of it. Right? It was GitHub. And they've used it everywhere. And it tells you a lot. What's great about Copilot is it's still your fault. You're the pilot. The Copilot messes it up. You don't get to blame the Copilot. It doesn't work that way. But it is a tool to interact with. You go back and forth, and this is the one area of this large language model space where we're seeing real performance gains. I talked to a lot of PMs. We've done a bunch of case studies around this, and we're seeing 25, 30% productivity gain. The developer's still very much in charge, but they can write more code with less remediation in less time. And that's compelling. It's becoming a tool that's kind of not optional, and it's obviously continuing to improve. I mentioned OpenAI briefly. This is a company that was formed in 2015. It was under the banner of being open source and available to everyone, except that they didn't actually do that. They made GPT-1 in 2018. By GPT-2, they already decided it was powerful enough that they wouldn't release the code base. GPT-3 in 2020, 3.5 in 2022, which is when ChatGPT was released, and they went from 0 to 100 million users in 2 months. And we're now in the crazy of a new hype cycle. Microsoft, of course, invested very early in OpenAI. This originally was supposed to be funded by tech billionaires like Peter Thiel and Elon Musk, except they lied and didn't actually fund them. Even just the past couple of years ago, Elon was saying, well, I put $100 million into OpenAI. That is not true. He put about $20 million into OpenAI and 6 Teslas. And that wasn't enough money. They managed to convince all these scientists to come work for this entity, but they were barely funded. And then Kevin Scott from Microsoft came along and said, make you a deal. We'll put $1 billion in, but you have to move all your workloads to Azure, which is kind of a clever trick by their part. Here's $1 billion. Now give it back to us in average Azure utilization. And then when they ran out of it, it's like, here's $2 billion more. You get to give it back to us again. And when ChatGPT came along in 2022, it's like, here's $10 billion. We'll help you with the amount of compute you need. And now it's running all over the place. Microsoft obviously has grabbed onto the Copilot name because it's a better name than they could possibly think of. Our friend Satya Nadella actually wrote a letter to the company in January 2023, an internal letter where he said, here are the OpenAI APIs. Every team needs to work on these and add them to their products. And so internally, there's more than 200 Copilots, which is terrifying. We only know about a few of them. Most of them will never see the light of day because they're mostly repeats of each other. But what Uncle Satya just did was make several 100,000 people all march in the same direction to explore a technology. Microsoft is heavily committed in this space. It'll be interesting to see what happens. Now, I've been working in the industry for a long time. I know a hype cycle when I see it. Gartner, which is this research group, came up with this term, hype cycle. It looks like this, that we have a technology trigger. That technology trigger leads to over-excitement, over-exuberance of possibilities that goes rocketing up the peak of inflated expectations. And no software can qualify for that. And so then it comes back down into this trough of disillusionment. That's the dot-com bubble. The internet's going to change everything. And we hyped it up to the point where by 2001, it was clear it could do some things, but not everything. And we had the dot-com bust. And so AI is going through this cycle, particularly large language models, recognizing that AI is a blanket term. But large language models are currently on a ride. And I would argue we're already past the peak, that we're somewhere down, see if my pointer works, here, on the way down. Now, I'm hoping it doesn't get too far down because there is value in this technology. And sometimes when the trough gets a little too deep, dumb things happen. Legislation starts to cripple the ability for the technology to innovate. And companies avoid, it becomes not a respectable thing to use. We wouldn't touch this. Think about what happened to things like BitTorrent and blockchain. So we are on a ride right now, looking for the edges of what's reasonable and usable. Your engineering habits are still important here. Using technology responsible is still a key part of the overall equation. There are no simple answers, and we're exploring as quickly as we can. If you're willing to just ride the hype cycle, it's a good way to make a pile of money, perhaps. I think OpenAI is going to do pretty well, but they are kind of a one-trick pony. You know, in a gold rush, you look for who's selling shovels. And it's the big tech companies, right? All of this stuff has to run in the cloud, so the cloud vendors are happy because we're going to have to run all this stuff on their gear, and so they're going to make money whether it works or not. But for the rest of us, choose carefully. Take your time, test thoroughly. The software is remarkably resistant to testing. And I will talk a little bit about the AGI side, or the super intelligence. This is a science fiction trope, right? It has never been real. It is what writers have created. Problem is that we've had characters along the way, whether it was HAL or Terminator or Johnny Five or Ultron and Jarvis. They are science fiction. Large language models are like parrots. They present language as if there was understanding, and there isn't. It's a statistical model of response. There are good books in this area if you actually want to dig into what intelligence and software would look like. I find Roy Blatt's book particularly compelling, a very challenging read, but he does break down the greater complexities of what an intelligence would actually look like. And if there's anything you'll carry away from a book like this, it's that we're not even close. Now, there are forces inside of this space that are very keen to raise money on the back of that not being true. And artificial intelligence has always been a marketing term, so don't be surprised that they market on this. But look at the facts and use the tools accordingly. It doesn't mean it isn't dangerous. All powerful tools are dangerous. It also doesn't mean it hasn't done good. In some ways, I feel like large language models have overwhelmed the conversation. There's more important things going on in this software that's really going to shape the next decade for us. One of my current favorites is AlphaFold. So these are DeepMind. They're now owned by Google. And they did the Go solution, AlphaGo, where they found a way to use a generative AI model to play the board game Go better than humans. But they went on to do something more important with it, and it's around protein folding. So this is a very essential part of biology, is the ability for cells to create new proteins, to create new life and systems. And it's incredibly complex. They estimate there are 10 to the 300th possible protein folding combinations in contemporary genetics. And so there's been a contest for many years called the CASP contest to help build technology to understand protein folding, to find new medicines, to understand how disease works, to improve cellular construction, really essential biological concepts. And it was the AlphaFold folks that got involved in 2020. Actually, 2018 was the first time, and they got the best results of any group ever. And this was real open source software. So the next year, 2 years later, they do the contest every other year. 6 teams were able to use the software and bump the numbers up even further. They started to build new protein folding structures. This year, virtually every team that computes in CASP uses a version of AlphaFold. So new science is emerging from this. Again, it's not always about the language. We've been kind of buried under that. There are more important things going on in generative AI that are going to have bigger impacts down the way. Now, it's not that everything in LLMs is useless. The tokenization of language has opened up an opportunity for us to translate more effectively. Translation tools are in the midst of being transformed right now. They convert language into the token strategies that LLMs use and then can deconvert it into a different language. So it's become relatively trivial now to bounce between languages fairly well. And that's all software that's being written in the next few years. That we can come to expect to be able to speak our own language to anyone who will hear it in their language, speak their language back to us, and we'll hear it in ours. Right? That Babel fish from Hitchhiker's Guide to the Galaxy, it's appearing. It's imminent. I do think that the generative AI technology is going to have a huge impact on video games. Now, if you're immersed in the video game industry, it's a multi-billion-dollar industry. It's actually bigger than movies. Billions and billions of dollars built on video games. The problem is that current generation compute, whether you're talking about a high-end PC or a top-of-the-line video game console, have so much computing power today that it takes 300 to 400 people and 18 months and a couple of $100 million to make a top-tier game, which means you have to get a billion-plus return on it for it to be profitable, and it's too high of a risk. If you're in the gaming space, you'll notice that for the most part, our top-tier games are last year's games version X, because it's the low-risk way to build new games. Part of what makes a game expensive is that you have to do an extensive amount of voice acting. So you're writing out all the scripted choices for playing a game. Every storyline is detailed out, and then it's all voiced. With LLMs, we could be generating a lot of that. So you generally have plot directions and communication that needs to happen, but you don't have to figure it out word for word, and you can generate the voices for that. So this should lower the bar for making more advanced games. The same with visualizations. We have better and better generative AI visualization tools. So one of the reasons the gaming industry is going through a meltdown right now is that leadership is looking at these technologies and saying, why are we making software the way we are? And they're pulling back and rethinking. This is going to emerge in the next few years. I think it's going to be a revelation in games because it's going to open up the door to making many more games. That smaller group of people are going to be able to build bigger and better video games and be a part of this great story of the way that we entertain ourselves. There's an interesting idea here of changing the way we create a UI. We can now interpret people's behavior fairly well. Most devices now have a camera on them. We have generative AI models that can estimate people's behavior. I've seen this in retail outlets where they're putting cameras on coolers. And the data they're able to gather from that camera now is your gender, your likely racial profile, your age, and your mood. I saw a demonstration of a transparent LCD panel cooler where as you walk towards it, the software had assessed who you are and presented an ad on the glass of the cooler tailored to you. It was creepy. But that's where we are technologically. But it speaks to an idea that what if all our UXs were dynamic? We already typically build at least 2 UXs per piece of software as it is. You build one for the beginner with lots of tooltips and drag around things to help them understand how to use the software, and one for an expert with shortcut keys and quick tips and quick ways to move through the app. So you already typically build 2 UXs. Well, what if they were only describing their intents, and most of your screen now is dedicated to showing them the results, but you were also using the ability to interpret the user, say, how frustrated is the user? Does the user understand? Are they looking in the right place? Can I adapt the UX to the user as I build? What if everybody's user experience of my software was specific to them? That how I'd interacted with the software before, what features I needed, those were presented first. So dynamically shaped software. We have the tools for this now. We're still a few years away from going down this path, but as these language models get, and these generative AI models get smaller, that we can run them on the local device, I think we're going to get to a place where we can change the way we construct UX, that we literally react to how the person uses our software, and we emphasize the things they want so that every experience is unique to them. Let's talk about what happens to the smartphone going forward, because this slab of black glass has now been the same for almost 20 years. It's ripe for replacement. I don't know how many cameras we really need. 2 cameras, 3 cameras, 4 cameras. Like, I got enough cameras. We don't want it too much bigger. We can barely hold it in our hand as it is. I don't know how much bigger a display I want. Okay, we're folding. Now there's a trifold. Like, I'm done. Let's do something else. And you're starting to see some efforts in this direction. Now, for a while there, Apple's thing was the way, but I think Tim Cook's now figured out $3,500 is a lot of money, and in the end, it's still virtual reality. And virtual reality can only take you so far. Really, what you want is augmented reality. I want to let you still be in the world, but I want to augment your experience. Now, Microsoft attended this with the HoloLens, but they've been waylaid too. This was the Trimble version. This was designed to be working on construction sites, but it never really went that far. We are seeing success with some augmented reality sets like HoloLens, but in particular verticals. So in industries where technicians need to maintain equipment, having all the information directly in front of them as they're interacting with the machine is pretty powerful stuff. These are expensive devices, and they cost a lot to operate. So they're only existing in particular verticals so far. They're not a general consumer device. And the remarkable pieces of technology, Microsoft chose to put the entire computer and its battery in the headset, which is why it's so bulky. It's just a tremendous amount of compute, and it's 6 years old. So they still are only selling HoloLens 2s, and they only sell them to existing customers now. They're running out of them. They never made the HoloLens 3. They got it to prototype phase, and then they stopped. It wasn't good enough. Now they apparently are waiting on hardware, but the team's been cut back dramatically. The area of innovation for augmented reality now is Meta, which is funny because when they rebooted as Meta and they went all in on VR. They had the Oculus sets, so they went heavily down the Quest headsets. These are VR headsets, and they're the best in the industry. They're well priced, but they are still just VR. But recently, they did a bit of a sneak peek concept view of some augmented reality devices, a device called Orion. Getting closer to glasses, but the big innovations here are these 2 other devices. The first was they've offloaded the compute into a puck. It's wirelessly connected to the headset, so now you're carrying a puck, it's got the antennas and the battery, and you don't have to wear it on your head, which is nice. It makes the set a little bit lighter. And the wrist device is actually reading the nerve endings in your arm. So when you flex your fingers, the device can see that, and that's your controls into the augmented reality space. Now, this is not a commercial product. This is a prototype. They guess is about $25,000. And they're years away from actually making a production product. But it brings back, even though the focus has been on artificial intelligence lately, augmented reality has been out there as a new way to think about the user interface and the way that people interact with their devices. So we're back to the idea of I wear a pair of glasses and my world is augmented. We all know as developers that the correct amount of screen space is more. So what if every surface could be screen space? That I'm literally just attaching screens wherever I am, wherever I look. They stay in place relative to my head so they don't follow me around. But I get to interact with that device. And for the first time in a very long time, this might be an actual space that we can program in. So instead of working on a PC and then looking at what you've built through the glasses, what if you just were wearing the glasses and interacting with a 3D space and also able to program with it? That short dev cycle of being able to iterate in the augmented reality space sets us up for a Cambrian explosion, a sudden expansion of software in the space, once the headset is good enough, because there are real challenges here. This is a better way to interact with your phone in the sense that often we are holding it up as an augmented reality interface and doing this. Actually just having it on so you're always looking through it would be more effective. The fact that I would always know your name because the headset told me. The idea that we could negotiate a contract, each wearing a pair of glasses like this, and the recording of our agreement and handshake becomes the contract. That the device is in the agency position. It knows what we're talking about. Hey, you up for lunch tomorrow? Yeah, let's look into it. And the software takes over and figures out whether lunch is going to work for us. In fact, I think a lot of the work that we're doing with LLMs and other AI-related technologies augments this technology as well. The next 10 years, this technology will emerge in a meaningful way, and it should change the way we write code. It should change the consumer interface, although that will come last, right? The smartphone became popular in large corporations in the form of the BlackBerry for almost a decade before the iPhone. 10 years it takes to mature a technology enough to make a shift like that. It might be shorter, but it's also not going to be first. So the focus to try and make this a consumer device is a mistake. If you really want to be on the leading edge of what AR can do, find the info worker solution. What's the replacement for a Word document in augmented reality? What's the replacement for a spreadsheet? How can I be a more effective ERP operator? You solve that problem. You sell a lot of headsets. Then the consumer product will emerge, and the gaming will emerge, and these other opportunity spaces will happen. I feel like Meta's got a lead right now. What they've presented with the Orion really as a concept headset is interesting. They're not alone. Snap has their new Spectacle 4s, which they've gone with a completely integrated design. They're not using the pucks and things. The difference with this and Orion is Orion you cannot get. You can only admire. But if you've got the money, you can order the dev kit for a Snap Spectacle set now. It's 100 euros a month, and you have to commit to 1 year. But it is, again, integrated augmented reality devices. So we have another wave in front of us. Maybe we're a little ahead. The first 2 years are always slow. But by early 2030, which is only 6 years away, we should expect these to become more relevant. It will happen faster if smart people figure out the solutions that are going to drive it into business. Okay. That's pretty grounded stuff. Let's get a little more speculative. Should we talk about quantum? So, quantum computers are not having a great time right now. Their real breakthrough was in the 2018-2019 timeframe. This is the IBM Q. Most of the hype that you'll hear about quantum computers focuses on encryption. Don't worry about that. It's not actually that interesting. It's a way to stop the conversation about quantum. There are way more important problems. We are already moving transport layer security, TLS, to a non-prime based encryption strategy with asymmetrical keys, which will be completely quantum resistant. So the encryption solutions are already upon us before the quantum computers have really come to pass. And the quantum computers to be necessary to break RSA 4096 encryption is so robust, they're probably decades, if ever, anywhere near. These are very flaky devices. This is the Sycamore made by Google. They call this the chandelier, because the electronics hang downward and they have to be super cooled in liquid helium. Liquid helium is not fun stuff. It's very dangerous stuff to use. You have to pre-cool your cryocooler with liquid nitrogen first to be able to get down to the millikelvin temperatures of a liquid helium tank to operate these machines. This is colder than any known spot in the universe. one fraction of 1 degree above absolute zero. Bring layers. Also, when you lose control of your liquid helium, it expands 30,000 times and turns into a gas, it will blow a building apart. So the largest expense in most quantum computer laboratories is the venting systems to move that liquid helium when it gasifies. I bring up Sycamore because this was the first attempt at quantum supremacy. This was a device made by Google in 2019. It's a 54-qubit machine, although the trial that won the award was 53 qubits because one of the qubits was broken. Did a 200-second run to do what's known as a quantum random number problem with a known outcome. They solved it in 200 seconds. The guess was 100, it would take 10,000 years of the classic computer, although subsequently IBM found a way to solve it in 2.5 days with a supercomputer, which is still a lot longer than 200 seconds, but okay. The Chinese have their own approaches. This is the Zhuzhang photonic quantum computer. They tackled the boson sampling problem. They said it would take about 2 billion years to do that with a classic computer. They tangled 113 qubits to run it. These are all sample problem spaces. And then again, IBM with their Eagle and Osprey and Condor processors, progressively larger. The largest quantum computer that exists today is in New York. It's a machine called the IBM Quantum System 2. There is exactly one of them. It has the largest cryocooler in the world, and it takes about 6 weeks to turn this machine on. It takes a long time to get down to 300 millikelvin to actually get it to operating temperature. It's got 3 chandeliers in it. So it's flaky and complicated. There's about 6 different architectures that are working for quantum computers right now, different ways to make qubits. There's no consistent pattern. These are very bespoke machines. You have people with white lab coats that take care of them and worship at the shrine of quantum computing. But let's talk about real problems we could address with quantum computers, not just breaching encryption. What could we really do with quantum computers? And most of the most important problems in quantum computers are in the quantum chemistry space. So let's talk about nitrogenase. So this is an agricultural space. So we know in agriculture, for thousands of years, as humans were growing crops, that you had to rotate the crops. If you grow wheat in the same place of the ground year after year, the wheat gets smaller and weaker as the soils get depleted. And long before we learned how to make industrial fertilizer, we learned that if you rotate between different crops, you can replenish the soil and keep using it over and over again. But since World War I, civilization has developed through the Fischer-Tropsch process, or the Haber-Bosch process, this ability to affix nitrogen. It's actually 1% of all the energy we consume is to make fertilizers for agriculture. It also makes explosives because of course it does, which is why it was actually developed during World War I. The Ottoman Empire was running out of gunpowder, so they came up with this mechanism to build ammonium nitrate, which makes for pretty good bombs. And it happens to also feed plants. Meantime, we have the nitrogenase enzyme. So this is a rhizome that grows on the bean plant in its roots. So this is why you rotate crops. You grow a crop of wheat, and then next year you plant the beans. You harvest the bean pods off, that's your food. You take the rest of the plant and plow it under. And this rhizome that's grown on the roots is filled with nitrogen. And so that rejuvenates the soil. So the way that it does this is with an enzyme called nitrogenase. We've been studying this for about 200 years. Somehow, at plant energy levels, a catalytic reaction between iron atoms and molybdenum atoms inside of this enzyme pulls hydrogen off of water from the atmosphere and nitrogen out of the atmosphere and makes ammonia in a plant, quietly. If we could figure this out, we could make fertilizers for far less energy, much more localized. It's a 2 to the 140th compute problem, which is a little more than the number of atoms on this planet. And so classical computers have not been able to figure it out, but a mid-sized quantum computer should be able to crack it, a much simpler problem than 4K PGP cracking. And if you solved it, you'd make a huge difference in the world. Battery technology could benefit from quantum computing for the same reason. We currently innovate on batteries through alchemy. We just keep repeating practices and minor alterations and testing the results, and if we get better results, that's a better battery. We don't actually understand how batteries work at the deep level. We just keep mixing them up and trying to do better. Same for superconductors. In the 80s, we found that cupric oxides, particularly this one, barium yttrium, when cooled to liquid nitrogen temperatures, become superconductors. We've learned more about superconducting. We understand it's now a phase state of matter, which is a combination of temperature and pressure and structure of those atoms. Quantum computers could tackle these problems and help us build higher temperature superconductors. But you'll notice that all these quantum chemistry problems that I've talked about are very deterministic. Once you've solved them, you kind of solve them. You don't really need to solve them again. How many quantum computers do we really need? 6? Which of course leads to that old line from Thomas Watson, one of the original CEOs of IBM, when they were going out to sell the first mainframe computers. He thought maybe there's a market for like 5 of them. He was wrong. They sold 22 on that trip alone. But that was back when mainframes looked like this. Right? They were kind of bespoke machines. This is the 1950s. This is before we had silicon substrates and we were making ICs. This is when we used relays and vacuum tubes, and like every computer was unique. You had people in lab coats that took care of them. They were bespoke. They were kind of like this thing. Right? The early mainframes of the 1940s and 50s, we were still feeling around for what the proper bit was. We hadn't found the right way to do it. That's exactly where we are with quantum computers. Transmon architecture that's inside of the Q2 is interesting, but it's still a very challenging way to make a qubit. If you look at the original transistor, this is it. This is a germanium transistor made by Shockley et al. At Bell Labs. It's about this big. It's hard to imagine an M4 with 25 billion of them, right? This is a tricky thing to figure out. Now, here's the funny part. Shockley, one of the designers of the original transistor, had the idea that silicon was a better way to go. And he formed a company called Shockley Semiconductor in Northern California, in an area we now know as the Silicon Valley because of these people. And he was starting to do experiments with, can we make semiconductor silicon? And he used time on these mechanical mainframes to compute the likely elements that could be used to dope the silicon to make the substrates to build the first ICs. So it took those archaic computers to render the model to be able to build what would become the semiconductor. And then many of his team left Shockley to form Fairchild, and many of them left that to go to Intel with Noyce and Gordon Moore that ultimately leads to the CPU. So they couldn't see this, but they found their way there. And I wonder if we're not going through the same thing with quantum computers at this time, that we're still feeling around for the right qubit, and these bespoke, unreliable machines might be the computational engines that lead us to the more reliable qubit that then allows it to open the door and expand the potential utilizations of it. Now, we're down to the last few minutes here, so I want to talk about what's next. And the reality is, of course, that I don't know. I've asked very smart people. I believe in William Gibson's idea, the future is here, it's not evenly distributed. So I've been able to go into some corners and find different things. But the one thing I've heard over and over again, the one truism that I find is that largely it's up to us. We make the future. We get to choose what happens next. I hope we choose well. Thank you for coming to talk to me. We'll see you again.